Yes, I was saying that they won't just sell to you in land anyhow. No. Same thing. People now are more educated. They won't just accept risk in any way. No, no, no. So that's why these boundaries keep moving down. The negligible risk keeps on reducing. Okay. So that's the figure. Even in the textbook, that figure is there. Okay. They just explain it further in the textbook. They say the width of the triangle reflects the costs. The costs of ensuring risks do not result in incidents or accidents. Costs are incurred by risks at the top of the diagram. The lowest costs by risks at the apex of the triangle. Okay. And what I've explained is also said there that the boundaries between the regions are not fixed, but depend on how acceptable risks are in the societies where the system will be deployed. Okay. This varies from country to country. Okay, as I've explained. Now, and okay, and maybe just to make it more clear about these boundaries pushing downwards. Okay. Even for rare events, for example, if the cost of cleaning up pollution, you might have a company, you might have an industry that pollutes the environment, maybe pours out some dirty chemicals. Now you might find the cost of each and every time the chemicals are poured out, of clearing up. You might find that the costs of that are actually less than the cost of making of creating a system that automatically prevents this pollution from happening. Okay, that's the example they give. But still, because of how people are, it may not be acceptable for people to just see the environment being polluted and then you say you're going to clean up. Okay, so sometimes there are all those different factors that come in. Okay, different factors come in. So all those do affect. As I've told you, people are getting more and more aware. Okay, so public and media will not tolerate such accidents. Okay, clearing up the damage rather than preventing the accidents is no longer acceptable. Okay, events in other systems may also lead to a reclassification of risk. Okay, for example, risks that were thought to be improbable may be classified as intolerable because of external events. So things keep changing. Different factors change different things. Okay, some countries that never had tsunamis before, now they have them. Some have never had earthquakes, they have them. So all those affect, and same thing with systems. Different things happen now. Okay, we didn't have as many hackers and attackers as before. So you're not going to really, the systems are not going to remain the same. Okay, so that's about that, and also about the social acceptability of risk. Okay, this thing takes some time to change. I don't know why. Okay, so the next is risk assessment. Remember, I'll just go back still so as to keep us focused on how we are moving. We skip risk decomposition. Just a second. Risk identification, analysis. Okay, no, we didn't skip decomposition. Okay, so risk assessment. Estimate the risk probability and the risk severity. Okay, so once you have now looked at these three categories, okay, it's normally possible to do this precisely. So relative values are used, such as unlikely, rare, very rare, high, etc., etc. Okay, the aim must be to exclude risks that are likely to arise or have high severity. And this is now like an example is the insulin pump. This is its assessment. Okay, this is the assessment for the insulin pump. You can look at them individually later. Okay. Now, so the risk assessment really is once you've finished the analysis, then what you've come up with, for example, here is the risk assessment. Now, like for the insulin pump, what you've come up with after you've done your analysis. Okay, so next stage is the risk decomposition. Decomposition, remember, please don't get lost. Identification, analysis and classification, decomposition. Okay, is the next one. So risk decomposition. Okay, so you discovering the root causes of the risks in a particular system. Okay, so now you've known the risks, you've gotten their categories, but now you have to discover the root causes. Okay, there are different techniques used. We have the inductive bottom-up techniques, where you start with the proposed system failure, and then you assess the hazards that could arise from that failure. Or you can have the deductive or top-down techniques, where you start with the hazard, and then you deduce the causes of this. Okay. Let us have a look at fault tree analysis is an example of a deductive top-down technique, and we shall see it in this diagram here. So here you put the risk or hazard at the root of the tree, and then you identify the system states that could lead to that hazard. Okay, and a better way to explain this, because here they don't really give it in detail, I will refer you to this very book here. Let us look at it. Page 13. Okay, page 13. This is page 8. Okay, right here. So here they really give the detailed explanation, okay, of what we've been talking about. Okay, they give a detailed explanation, because here they say you put the risk hazard at the root hazard at the root of the tree, and then you identify the system states that could lead to that hazard. And this is exactly what is being done here. Beginning with the hazard of incorrect insulin dose administered. Okay, so here they explain that there are 3 conditions that could lead to the administration of an incorrect insulin dose. Okay, the 3 of them are here: incorrect sugar level measured, or correct dose delivered at the wrong time, or delivery system failure. Okay, and then so the left branch, then now so you continue going on further. Now going on further, the left branch of the fault tree concerned with incorrect measurement of the blood sugar level identifies how this might happen. This could occur either because of the sensor that provides an input to calculate the sugar level has failed, or because the calculation of the blood sugar level has been carried out incorrectly. Sensor failure, sugar computation error. Okay. And then if you go further in that, now because now this one ends here, but then it continues further here on this arm here. And the sugar level is calculated from some measured parameters, such as the conductivity of the skin. Okay. Incorrect computation can result from either an incorrect algorithm or an arithmetic error that results from the use of floating point numbers. So you can see we have gone right up to the root cause. Okay, and then I hope this page is clear to all of you. The central branch of the tree is concerned with timing problems and concludes that this can only result from system timer failure. Okay, there you are, timer failure. And then the right branch. The right branch of the tree, concerned with delivery system failure, examines possible causes of this failure. This could result from an incorrect computation of the insulin requirement or from a failure to send the correct signals to the pump that delivers the insulin. Okay, so you can see, so I hope you see the step-by-step analysis, okay, of the fault tree. Insulin computation incorrect or pump signals incorrect. Again, an incorrect computation can result from algorithm failure or arithmetic errors. Again, you can see that here, okay, up to the root cause. That's what they call the fault tree analysis. Okay, very well explained here with an example of the insulin pump. Okay, I also want you to take note, however, of these fault trees. The fault trees are also used to identify potential hardware problems. They explain that further down here. Okay, that fault trees are also used to identify potential hardware problems. Hardware fault trees may provide insights into requirements for software to detect and perhaps correct these problems. For example, insulin doses are not administered at a very high frequency, no more than 5 or 6 times per hour, and sometimes less often than this. Therefore, processor capacity is available to run diagnostic and self-checking programs. Hardware errors such as sensor, pump, or timer errors can be discovered and warnings is issued before they have a serious effect on the patient. I want you to take note of that as well. Okay. Okay, so we can go back to the, let me just go back to the PPT. Okay. Okay, so that's the insulin pump fault tree. It's okay, it's the fault tree analysis, but then we're looking at the insulin pump particularly as our example there. Okay. So the next share, let me share my screen. Okay. So we have finished risk identification, risk analysis and classification, risk decomposition, now risk reduction assessment. Okay, we have to be systematic in this and don't get lost on that. Okay, so that's the next one here, the risk reduction assessment. So the aim of this process is to identify dependability requirements that specify how the risks should be managed and ensure that accidents or incidents do not arise. So all that we have been doing, all the steps we have been taking, they are all they all come up to this point. Okay, the dependability requirements that you're going to come up with, okay, to reduce your risk. And these involve 3 risk reduction strategies, of which we have risk avoidance. Okay. Risk avoidance, the system is designed so that the risk cannot occur. Okay. And then we have risk detection and removal. The system is designed so that risks are detected and neutralized before they result in an accident. And then we have damage limitation. The system is designed so that the consequences of an accident are minimized. So these ones here are not new, at least. Okay. You have them there. But then also the designers of these systems may use a combination of these approaches. Okay. Because of course you're not going to say you're going to only use one. depending on how your system is and the risks that you've come up with, you may have to have different ones. Okay. Okay. To the next. Yes, that's what they talk. That's the next. Well, that's what they talk about next there. Okay, so you can have a mix of risk reduction strategies. Okay, and they give those examples there. In a chemical plant control system, the system will include sensors to detect and correct excess pressure in the reactor. However, it will also include an independent protection system that opens a relief valve if dangerously high pressure is detected. Okay, so you can mix. You're not tied to one. Okay. Not tied to one. Okay, so we talked about this. We saw this already from the. Just explained them further here, but we had seen them already from the what? From that from the function analysis. So some of the safety requirements of the insulin pump. So these are examples of safety requirements that you've come up with. Remember, we're coming up with dependability requirements, and remember, dependability involves safety, security, availability, and reliability. So among the dependability requirements, we have safety requirements. Okay, safety requirements of the insulin pump. The examples are here. SR1, the system shall not deliver a single dose of insulin that is greater than a specified maximum dose for a system user. So that one is a safety requirement. So the system, even if it makes a mistake, as long as they don't go beyond a certain maximum, in that case, it's not as dangerous. Okay, so that's one safety requirement that can be defined there. So something may go wrong, it gives the wrong amount of a wrong dose of insulin, but then not going beyond a certain maximum. Okay. Safety requirement 2, the system shall not deliver a daily cumulative dose of insulin that is greater than a specified maximum dose for a system user. Still, this is just further making it even further safe. Okay, it's really just a total sum of the first one, total sum of the many single doses, okay, not going beyond a daily specified maximum, System requirement 3, the system shall include a hardware diagnostic facility that shall be executed at least 4 times per hour. So this insulin pump looks like it's doing nothing when it's hanging over someone's body, but it's actually having the diagnosis going on. Okay, so the hardware has to always be checked on. If there's something wrong, an alarm goes off. Okay. Right. And then safety requirement 4, the system shall include an exception handler for all of the exceptions. Okay. So once you have those algorithmic and arithmetic errors, and then the exception handlers are going to help to deal with that. Okay. Safety requirement 5, the audible alarm shall be sounded when any hardware or software anomaly is discovered, and a diagnostic message should be displayed. So the alarm, and it has to be audible and visual, okay, because there's a display as well, so that action is taken. Safety requirement 6, in the event of an alarm in the system, insulin delivery shall be suspended until the user has reset the system and cleared the alarm. So you see, the system even just goes further with safety. Senses the alarm, it also it's careful about how it's giving out the insulin. Okay, it's careful about how it's giving out the insulin. Right. Safety specification. Safety specification. Remember, if I go back up, we looked at risk-driven specification. Now we're looking at safety specification. Okay. Although for the safety specification, we actually looked at it. We looked at some of them the last time, because it deals also with that standard IEC 61508. Okay. Yes. So the safety requirements of the system should be separately specified. These requirements should be based on an analysis of the possible hazards and risks as previously discussed. Okay. Safety requirements usually apply to the system as a whole rather than to individual subsystems. And in systems engineering terms, the safety of a system is an emergent property. So we actually we saw this. We saw yes, we saw this standard here. Okay, and this we were talking about this standard just in the past lecture. IEC 61508. It's an international standard for safety management that was specifically designed for protection systems. Okay, it is not applicable to all safety critical systems. So we saw this last time. That's so we shall not go into so much about safety specification. Okay, this standard incorporates a model of the safety life cycle and covers all aspects of safety management, from scope definition to system decommissioning. Okay, and that's the that safety life cycle. There's a picture of it there. Okay, the safety life cycle, starting from the concept and scope definition, hazard and risk analysis, safety requirements derivation and allocation. Okay, planning, validation and O&M and installation, safety-rated systems development, external reduction facilities, and then safety validation, installation and commissioning, operation and maintenance, and then system decommissioning. Okay, so the safety life cycle really of any system, of any system. Okay, that just shows that life cycle. Okay, and then the control system safety requirements. Okay, this one really just shows you the safety requirements where they apply. They apply to the protection system. Okay, these safety requirements apply to the protection system. The control system has its system requirements, but the safety requirements apply to the protection system. Of course, the protection system in the end is going to affect the equipment, and it's going to affect the control system. Okay. Okay, and then safety requirements, we have what we call the functional safety requirements and then the safety integrity requirements. Okay, of which the functional safety requirements define the safety function of the protection system. They define how the system should provide protection, in other words. And in the safety integrity requirements, they define the reliability and the availability of the protection system. Okay, and they're based on, and we also saw this last time, they're based on expected usage and are classified using the safety integrity level from 1 to 4, which we saw the last time. Okay, right. So I did not want to begin security specification, so I'm going to, because we won't even have the time to finish it. So it's I'll do it next week. I'll do it next week. With time, I'm going to communicate when we shall have our first cut. I prefer we have it physically. Hey, permission again. Oh, sorry. Did I? No, I gave the permission, I think. We shall have I'll communicate. I think within next week, I'll communicate when we shall have our first cut, and also I'll see about the assignments. Okay. Yes. Otherwise, I hope and pray everybody is keeping safe. The recorded meetings, I think you contact Nansamba Rachel, because she's the one who codes. Okay. Yes, but otherwise, I hope everybody is keeping safe. Please do keep safe. You know what's happening. Yes, she has them. Good. She can share them. So please keep safe. You know what's happening. And also, I know you people have had a lot of juggling with your studies. That's a bit unfortunate. I feel sorry for you on that part. But I pray and hope that somehow you're catching up. You're catching up on those. Okay. Yes. Okay, and also I hope that apart from this course, you're also catching up on the other ones as well. Courses in time, and then go to the fourth year and also finish that, because you're not going to study forever. Okay, so please be serious with your work. The lecture can be shifted so as can all attend. In other words, the Friday lecture is more available. You're more available the Friday lecture. I don't know how possible that is, but I will communicate. Let me see. I will communicate. However, I'm just reminding you, once we start the physical lectures, then we shall have the first cut somewhere. I will communicate. With internship from 8 to 12. Okay, but Wednesday is actually the afternoon lecture. Eh? Wednesday is the afternoon lecture. And others have afternoon session for intern. Yes, I guess there's a lot of mix up right now. That's what I'm saying. I feel sorry for people. There's so much mix up. There's so much mix up. There's so much mix up right now, but we shall try to sail through as we can. Okay, we're going at a good pace. We're going at a good pace. We have covered already a good part of the work. Yeah, hopefully we shall continue going at a good pace so that we don't have to go too much into December. Okay, so that we don't have to go too much into December, and then people can have time to prepare for the exams. Okay. All right. Okay, please do keep meet. Yeah. Oh, yeah. If by the way, you can feel free. If you have questions, you can always feel free to ask me questions about the safety critical systems. Even if you have other questions, really, out of safety critical systems, feel free to ask me, because I'm more experienced with the life than all of you. Okay. I studied it a long time ago and finished. I've worked for a long time now. Yeah, so you can ask me really anything about the safety critical systems, even out of that. Because, coming to school is not just about learning what we are learning here. It goes beyond that. When you come into the working world, you'll see what I mean. It goes beyond just studying what's in class. Okay. Okay, have a nice Friday, have a nice weekend. Bye-bye.